All right, we back. Cool. Okay. I forgot to mention this earlier. I know that at least a couple people have to be at the school at a certain time. If you need to leave, just leave. That's, like I said earlier, lectures are recorded. I prefer that you guys be here, but I know that needs must sometimes. And we are probably not going to go all the way to 10:15 most of the time because that's just a long time, and I don't think we need that long. But if you need to leave to be on time to class, then by all means, you can keep us going on your phone, listen to us in the car on the way over, whatever. But that should not be an obstacle because I'm not going to be offended. Yeah, it's just a good housekeeping note there. Okay, so getting back into our talking about neurotransmitters. All right, so if you don't know exactly what a neurotransmitter is, there is about 100% chance that you've heard of at least a couple of these. All right, so what is a neurotransmitter? Let me get my view down here. There we go. Better. All right, so a neurotransmitter is a chemical messenger that neurons use to communicate at the synapse. We'll talk more about what a synapse is in a minute. But it is located in the vesicle of the axon terminal. Vesicle is this little sac-looking thing that carries neurotransmitters from neuron to neuron. There's about 100-ish types identified, and we're going to go over every single one of them. Joke. That's not going to happen. We're not going to do that. We're going to go over like 8 or 9 because they're the most important ones, and they do the most stuff. Let somebody. All right. All right, so we're talking about communication between neurons. So this is just a picture representation of what we just talked about. So you can see the sending neuron up there at the top, the receiving neuron down there at the bottom. Okay, so our vesicles. The vesicles are the little like bubble looking things in the sending neuron. You can see the little dots. The dots are the neurotransmitter. You can see it starts with that action potential, goes down, makes it all the way to the axon terminal. So the action potential triggers the vesicles to release the neurotransmitters into the synaptic gap. What's the synaptic gap? So the synaptic gap is that little space in between those neurons. So the neurons never actually touch. They come very, very, very close to touching each other, like microscopically close, but they don't actually touch. So key point here, key point because it's a like, okay. So important point here is that the neurotransmitter is like a key, and the receptor site, which you can see the little green things there in that receiving neuron, is like a lock. So you have to have the right key to open the right lock. So if you don't, like I said earlier, this is a selectively permeable membrane. It only lets certain things in. So if it is not the right thing, then it is not going to be allowed to bind to that receptor site. Once it makes it through that receptor site, it goes into the receiving neuron. That just gets passed along. So key point here is that, I think it's on the next slide. No, did we ever talk about reuptake? Yeah, reuptake. So reuptake is the idea that you can see here on if you can see here on number 4, the fourth little note here, so that after binding, neurotransmitters are reabsorbed or diffused out of the synaptic gap. So not all of that neurotransmitter is going to make it into that receiving neuron. Some of it is going to be diffused across that synaptic gap and just kind of go away. But some of it is going to get taken back up into that sending neuron. Now, this can become an issue if too much of that neurotransmitter is being taken back up. So if you have a condition like, let's say, major depressive disorder, so a neurotransmitter like serotonin might not be making it into the receiving neuron at the rate that you would like. So there's a type of medicine called SSRI, selective serotonin reuptake inhibitor, that sort of acts like a lid on that receiving neuron. So instead of allowing that neurotransmitter to get taken back up, it is going to sort of force it to stay in the receiving neuron so that you can have more serotonin in your brain. You don't feel as sad. That is one action that you can take. That's also non-controlled. So it's not going to, there's no chance of you getting addicted to an SSRI. All right, so some major neurotransmitters. So on most of these, you will need to know which one goes with which behavior, which part of the brain. Most of them are pretty straightforward. So acetylcholine, very easy. Anytime we talk about acetylcholine, we're talking about movement. Okay, so this is, like it says here, too much of acetylcholine getting taken into that receiving neuron will cause muscle spasms because if there's too much activity movement-wise, that's going to sort of lock you up. But too little causes paralysis. So we'll talk about how like a paralytic agent works in a minute, but it's implicated in Alzheimer's. So if you have too low levels of acetylcholine, that is one potential problem that Alzheimer's can create. Glutamate is one of the major excitatory neurotransmitters, which means that it encourages reactions, has a central role in learning and memory. So glutamate, there's a very good crash course video that goes along with this that's in our crash course video folder on Blackboard with neurotransmitters, I should say. I can link that in my message to you guys for this weekend. But glutamate, if you've ever heard of MSG, monosodium glutamate, a lot of people have MSG sensitivity. So if they eat too much ramen noodles, they will like have seizures because this is one of the things that glutamate can cause because it's excitatory. It can cause too many reactions to happen, and that causes a lot of problems. Also mess with people's memory because glutamate linked to memory. But the major thing you need to know about glutamate is that it is an excitatory neurotransmitter. The opposite of that is GABA. And so GABA, since it's gamma aminobutyric acid, is the whole neurotransmitter name. It is an inhibitory neurotransmitter. That means it prevents reactions from occurring. So how that pops up is in something like generalized anxiety disorder. If you don't have enough GABA, you are going to have, anxious thoughts, fears, things like that, because your brain is going through too much activity than it is intended to, and that can cause a lot of problems. Norepinephrine, you may have heard of its other name, which is noradrenaline. So it comes from your adrenal glands in your kidneys. It can act both as a neurotransmitter and a hormone. We'll talk about what the hormone is later. But it helps your body prepare for stressful situations. So the example I always use is if you're being attacked by a T-Rex, your norepinephrine is going to kick in. Norepinephrine as a neurotransmitter happens faster. So this is more like if somebody kicks a ball at you. So your stress response is going to kick in and say, hey, I need to get out of the way of that. Other roles it has: attention, arousal, and sleep. Okay. So sleep, it's more that it can mess up your sleep because obviously if you're trying to like calm yourself down, you don't want a bunch of adrenaline in your brain. Attention, it can increase attention. So one thing that in a fight or flight kind of situation, your pupils dilate, you're like more locked in on that particular situation because it might be life-threatening. So I mean, also when we use this term arousal, we're not just talking about sexual arousal, even though that is potentially a part of it. Arousal really just means arousal of any of your body's systems. So things like your heart beating or your lungs, increase respiration typically if you have too much noradrenaline. Hold on one second. Take care of this dog. All right. Norepinephrine, talked about that one. Serotonin. Okay, so we talked about major depressive disorder. Serotonin can help regulate things like appetite, aggression, and mood. So if you don't have enough serotonin, you're going to have trouble sleeping, and you're going to have issues with your respiration, and your mood is going to drop. So low levels have been linked to depression. We talked about the use of SSRI for treatment because you're limiting that reuptake. There's a bunch of different ways that you can treat things like depression. That is one way that you can do it. But again, it's also not controlled because the action of it is not to increase binding at receptor sites. You can't get addicted to it. You can, however, get addicted to dopamine. Okay, so dopamine plays a key role in attention, learning through reinforcement, regulating body movements. So irregular levels have been linked to schizophrenia and depression. So those are sort of opposite ends of the spectrum. If you have too much dopamine, you might have a psychotic episode, which is one of the characteristic markers of schizophrenia, schizophreniform disorder. Depression, dopamine is kind of known as one of your like happy neurotransmitters. It's part of your reward system. So if you get a rush of dopamine, it's going to make you feel good, which is one of the reasons that it's in drugs like cocaine and amphetamines. Now, why is it implicated in substance abuse? So as opposed to an SSRI, which just limits reuptake, dopamine and its agonists, we'll talk about what an agonist is in a second, but something like cocaine is increasing the amount of dopamine that is bound to those receptor sites. So it's not just limiting reuptake, it's actually increasing the amount of dopamine that's passing from sending neuron to receiving neuron. Now, the problem that creates is that your brain will adjust to that new increased level of dopamine to the point that you have to keep adding more and more of whatever substance that is to achieve that desired effect. So eventually your brain regulates, because it's very good at that, to the point that it is not normal until you take whatever drug you're taking. That's how you get addicted to it. Endorphins, similar action. So opioids, if you've heard of OxyContin, that's exactly what we're talking about here. But your body produces these things naturally. So what do endorphins do? They are released in response to pain. So you'll often see endorphins described when we're talking about like brisk exercise. Like if you are a big like runner or something, you get this like runner's high, these endorphins where you like don't feel pain. And that's what's happening. It's just an increased level of endorphins in your brain, which is being sent out to your muscle tissues. But you can also mimic the action of that with drugs like opiates. So like OxyContin is a painkiller, which is how people get addicted to it because it works the same way as dopamine does. Eventually, like your body will just adjust to the point that you have to have the drug to get back to normal, and then you have to keep adding more to get to the desired effect. And it just continues the cycle. Okay, so what we're talking about with agonists and antagonists. Okay, so an agonist increases the normal activity of a neurotransmitter. So something like example they use here is nicotine. So it mimics acetylcholine and causes the same activation. So it's getting more that acetylcholine to bind to that receptor site. More receptors are activated and more messages are sent. So it's not just limiting reuptake, it's actually increasing the number of messages. You can see the little lightning bolts down there at the bottom. There's more than there are on the antagonist page. So the antagonist is doing the opposite. So an antagonist is trying to block those receptor sites. And so I think, and a key distinction here is that like you can have, because we talked about excitatory and inhibitory neurotransmitters, and now we're talking about agonists and antagonists, which can kind of sound like the same thing, but they're not, because you can have an inhibitory agonist, something that increases reactions to slow down activity. So like if you have a GABA agonist, you're actually going to decrease reactions, but you're going to be increasing the number of, or the amount of neurotransmitter that passes into that receiving neuron. And then you can have an inhibitory, or you can have an excitatory antagonist. So something like caffeine, which I don't know about you guys, but I definitely had some of this morning. So an antagonist, and we'll talk about, we'll use caffeine as an example. Caffeine actually blocks the receptor sites for a neurotransmitter called adenosine. So what does adenosine do? Adenosine helps you relax. So we're going to talk about your parasympathetic nervous system later on in the chapter, but it does things like helps your eyelids contract, helps you slow down your heart rate, helps you slow down your respiratory rate to the point that you can actually like sleep and rest and let your body recover. So caffeine, what it does is stops that from happening. So instead of getting tired and getting sleepy, things like that, you will stay alert and you will stay awake, which obviously can be useful in certain situations, but is also kind of an issue if you drink too much of it, because your body is being prevented from doing the thing that it wants to do, which is rest. The example they also use here is like a paralytic agent. So we talked about acetylcholine, how too little acetylcholine causes paralysis. So if I were to have an antagonist that was blocking the acetylcholine from binding at that receptor site, I would then be paralyzed. I would not be able to move. All right. So now we're moving into expanding our conversation about the nervous system. So you have two types of your nervous system. You have the central nervous system and the peripheral nervous system. And then within those two categories, we have a bunch of different subcategories that we'll talk about. But the central nervous system is the brain and the spinal cord, because those are the two components of that. And that's pretty much the only thing you need to know in terms of the components of the central nervous system. Peripheral nervous system is everything else. So it's a little more complicated because you can see all the different divisions in our little flow chart up here. So you have a somatic nervous system, an autonomic nervous system, and then within that autonomic nervous system, you have a sympathetic and parasympathetic nervous system. And peripheral nervous system, just to reiterate this, connects the central nervous system to the rest of the body. And so your central nervous system is mission control, basically. And then the peripheral nervous system is everything on the outside. So I have nerves in my legs. So going back to our example from earlier, if I step on a Lego, there's information being sent from the nerves that are in my feet. I stepped on the Lego, it'll send that information up to my central nervous system. And then my central nervous system will communicate back out to my leg to, hey, take your foot off that Lego because it hurts. All right, your spinal cord, bundle of neurons that allows communication between the brain and peripheral nervous system. Okay, so your spinal cord is sort of the in-between phase. And it's incredibly fragile. All this is pretty fragile, but your spinal cord especially. So if you've heard of somebody getting like a spinal cord injury, that can lead to paralysis pretty easily because there's a whole bunch of nerves in your spinal cord, and they run to very important places like your legs. There's three types of neurons. We talked about the structure of a neuron, what they do, but there's three functions that they can serve. Your sensory neurons, which is receiving information from your sensory systems. So like you hearing my voice right now, sensory neurons in your ears are picking up that information, sending it to your brain. And then your interneurons, which is your interpreters, act as a bridge connecting your sensory and motor neurons. So if you're hearing me and you feel compelled to write down all the brilliant things I'm saying, your motor neurons are actually the neurons in your hand that would allow you to write or type or whatever, however you're taking notes, because I'm sure all of you are. That transmits information from the central nervous system to the muscles and glands. So that pretty much every neural signal you'll get follows that same process. So if my dog comes up and lays on me, which she is, I will, the neurons in my leg will feel, her like lay on me, send information up to my brain. My brain will go, oh, that's pretty sweet. And then it'll send my information out to my hand to pet her, because that's what she wants. All right. All right, so there is an exception to this. It's called your reflex arcs. If you've ever gone to the doctor and they hit you on the knee with the little hammer and your knee goes like that, that's exactly what's happening here. So without input from the brain, because sometimes signals are just too important to have your brain get much input, it will just send it to the spinal cord and right back out. And so this is an example they use here is like putting your hand on a hot stove. So if it touches a hot pan, your brain is really good at like processing meaning, but you don't really need to figure out what that means just yet. If your hand touches a hot pan, you really just need to move your hand. So the sensory neurons in your hand will send that information to your spinal cord. Your spinal cord will determine, okay, well, we don't need to inform the brain just yet. We really just need to move. And from your spinal cord, your interneurons, a signal will be sent out to your motor neurons to move your hand. So Later, the brain will process that event and will determine, hey, we probably shouldn't put our hand on any more hot pans. Because like I said, your brain is, when it comes to like actually like figuring out what certain things mean, that's your brain is going to process that, going to be in charge of that. So the question here is, why do you think the reflex arc evolved? Well, there's a few theories about this kind of thing, but there's a lot. Your body has a lot of mechanisms for things like fight or flight, and this is one of them. So like if you were being chased by a predator way back in the day, this would be particularly useful, because if you were, attacked or something, you'd be able to move without actually having to process what happened just yet. Okay, talking about the peripheral nervous system. Peripheral nervous system includes all the neurons that are not in the central nervous system. So everything that's not in your brain and spinal cord is peripheral. So nerves, when we talk about nerves, bundles of neurons, so a bunch of different neuron cells that carry information to and from the central nervous system. So think about an electrical cable, informs the central nervous system about the body's internal and external environment. So your nerves are always communicating to your central nervous system about what's going on, even if you're not fully aware of it. We'll talk about your autonomic nervous system later. But the central nervous system makes sense of that information and responds, sending information back through the nerves of the PNS. So central nervous system is really involved in interpreting all of this. And then your peripheral nervous system is largely responsible for moving your limbs and stuff. Okay, so two branches of this are your somatic nervous system and your autonomic nervous system. So your somatic nervous system includes both sensory nerves and motor nerves, because you can actually, well, I'll just talk about the motor nerves first. So me speaking right now, I'm controlling that. So I am, in my brain, I'm telling my mouth to move in a certain way. I'm telling my tongue to move in a certain way, so that sounds will come out that you will hopefully understand. So I am in control of that process. I'm gathering information from sensory receptors, controlling the skeletal muscles, responsible for voluntary movement. Okay, so I'm like reading what's in front of me and communicating that back to you. So all of that is my somatic nervous system. Example they use is like pick up a pencil, taking notes. Like those are all things that you are controlling. Your somatic nervous system governs that. But you also have sensory nerves. So if I am, if I hear a sound that I don't fully understand, and I, incline my ear in that direction, that is my somatic nervous system as well, because I am intentionally moving myself to try and hear or smell or taste whatever stimulus I am interested in. Your autonomic nervous system, as the name would suggest, happens automatically. So while you're here listening to this lecture, you are also doing things like breathing and digesting, and your heart's beating, and you're blinking, all that kind of stuff. So that is your autonomic nervous system that controls that. So your body is doing all these things automatically because it's learned to do that. So examples of the two divisions, you have the sympathetic nervous system and your parasympathetic nervous system. So sympathetic nervous system, when you think about like a person being sympathetic, you tend to think that they're like, oh, they're nice and they're like thoughtful and they care about others and things like that. And it's kind of sweet and gentle, but sympathetic nervous system is kind of the exact opposite of that. This is your fight or flight response. So example of sympathetic nervous system is if you are, being attacked, your pupils will dilate, so you can see better, assess whatever threat is coming at you better. You're increasing your respiration, so you're getting more oxygen to your tissues, increasing your heart rate, so you can get more blood to your tissues, you can run away, increases blood flow to your muscles. And most interestingly to me, processes that are not immediate are kind of slowed down. So if your autonomic nervous system normally would, so like your parasympathetic nervous system is the opposite. So it's your rest and digest system. So if your parasympathetic nervous system relaxes your bladder, so like you pee, in a crisis moment, your sympathetic nervous system is going to constrict your bladder. So if you had to tinkle right before somebody attacked you, all of a sudden, because of the more immediate threat, you're not going to have to tinkle as bad, because your sympathetic nervous system is going to be like, hey, we can wait on that. We've got to assess this threat that's right in front of us. That's basically how this works. Digestion, same way. You're not overly worried about working that cheeseburger you ate a little while ago through your digestive system if you are, if your life is in danger. Your parasympathetic nervous system is the exact opposite. So we talked about adenosine and caffeine earlier. So a neurotransmitter like adenosine would work in conjunction with your parasympathetic nervous system to kind of get that process going. So it constricts your pupils, so like makes your eyes close, decreases respiration, so your heart rate and your breathing rate both slow down as you are trying to go to sleep, hopefully. And then it also activates your digestive processes. So a lot of digestion, a lot of breakdown of the food that you eat, and getting those nutrients out to your cells happens while you're sleeping. So if you're trying to repair muscle tissue that you might have broken down doing something like strenuous exercise, that's one of the reasons that sleeping is very important, because it gives your body more time to repair those tissues that you might have damaged intentionally or otherwise. There's also, think about like if you get sick, this is why you need to sleep while you're getting sick, so your body can help fight off that infection while it's asleep, can devote the energy it needs to. All right, so the other option here is your endocrine system. So there's one main difference between your endocrine system and your nervous system, and that is the speed at which those reactions happen. So endocrine system, instead of using neurotransmitters and neurons, is going to use hormones. So hormones are chemical messengers released into the bloodstream that influence mood, cognition, appetite, many other processes and behaviors. So a good example of a hormone is something like testosterone. So testosterone is a hormone. It one of the things that it does, it helps sort of moderate aggression and growth and things like that, which is why as you're going through puberty and your testosterone levels or estrogen levels fluctuate, it tends to influence your mood and cognition, appetite, things like that. All those things change as your body is adjusting to the different levels of hormones that it is now producing. So in what ways are these similar? Well, they're both types of chemical messengers. The biggest difference is the speed at which they happen, and a hormone is going to stay in your system a lot longer. So we talked about noradrenaline. As a neurotransmitter, noradrenaline will react very quickly. So it assesses threats very quickly, and if you need to get out of the way of something, and if you need to process an immediately threatening event, noradrenaline will work as a neurotransmitter. But adrenaline can also affect you more long-term as a hormone. So if you've ever heard of somebody like getting injured, but not like noticing it at first, that's because, in a situation where they were like in shock or, doing something difficult, like playing in a sport, they didn't notice that they were injured because of their elevated levels of endorphins and because they had more adrenaline in their system at the time. Now, once that adrenaline wears off, you're not going to be feeling super great, but that is the difference of the action as a hormone and as a neurotransmitter. Okay, so hormones also come from glands. Glands, you can see a few of the most important ones in that graphic. The most important one, arguably, is the pituitary gland. It is in the hypothalamus or under the hypothalamus in the brain. We'll talk about that, what that is later on, probably next week. But the pituitary gland influences all of the hormones. It's known as the master gland. So probably the most important thing that it does, other than sort of dictating all the actions of the other glands in the endocrine system, is that it plays a role in regulating growth. So if you've ever heard of something like human growth hormone, your pituitary gland is what releases that, what controls the levels of that. So if you've ever heard of somebody who's had like gigantism or acromegaly, they have too much human growth hormone in their system. They have an overactive pituitary gland, and they typically die pretty young because your body is not built to sustain whatever amount of tissue is created by an overactive human growth hormone system. Your adrenal glands, as the name looks like, adrenaline, that is what adrenaline comes from, is your adrenal glands. On top of the kidneys, and they're involved in responses to stress, which makes sense. I'm talking about adrenaline. Cortisol as well. Cortisol is a very important hormone that we're going to talk about in response to things like school stress, not immediately threatening, but stressful nonetheless. And regulation of salt balance. Salt balance is incredibly important in your body. You have this thing called a sodium-potassium pump that pretty much powers all of your voluntary movements. So if you don't have enough salt, or if you have too much salt, that is going to be a particular issue. Okay. And then your thyroid gland, located in your throat, regulates the rate of metabolism. So you've ever heard of somebody having a thyroid issue, they might be overweight, they might put on weight very easily because that is, they might have too low of metabolism, and that is regulated by this hormone thyroxine. Okay. That is a good stopping point. So we are going to talk about the brain hemispheres, a little bit more brain anatomy. Next time, I will stay here for a few minutes to take any questions that you guys have on the first assignment, second assignment, what have you. But as far as lecture goes, that's all I have. If y'all need to bounce and get to school, that's totally cool. But I'm going to stay here for a minute or two and hang out in the chat, and we can figure out what to do next. If y'all need to leave, I will see y'all next week. But yeah, I'll hang out for a minute.
Hey, so I missed some notes, and I was trying to go back and not watch the entire video. How do I find just the slides you get?
So the PowerPoints are in, I think, your course content folder on Blackboard. It'll just say PowerPoints, and then they're organized by chapter.
All right, thank you.
Yes, sir.
Oh, and should we be doing the little quizzes? I forgot what they're called.
Yes. So learning curves, I have them do is the same day as the test, which I am not 100% sure about when that's going to be, just because we got a late start as a class. But yes, you can certainly, and I would at least try a couple of them just so you can kind of get used to it, and just so we don't have any issues with people turning things in late. But I put them close to the test on purpose so that you guys can use them as review if you want to. But they're not due until the day of the test.
All right, thank you. That's it.
Anybody else got anything? All right, if y'all have any questions that you don't ask now, feel free to email them to me. But other than that, I will see you guys next week.